So I think we can start. So good morning, good afternoon, good evening, everybody. So welcome in this webinar, where we are very happy, glad to introduce you the low-level nutrient analysis in seawater. And the goal today is to cover what are the main challenges, methods, and solutions related to seawater testing. For the next slide, please, Antonella. So this session is recorded and the link will be shared with the attendees. We please ask you to use the Q&A session at the end of the presentation to address, where we address all the questions from you. And please keep your microphone and cameras off. Duration of this webinar is approx 40 minutes with around 15 minutes Q&A session at the end. The speakers will be Antonella Orella, our Senior Application Specialist, and myself as a Product Manager at KPM Analytics for wet chemistry testing. Now I'm very happy to give the stage to Antonella that will start presenting the presentation and explaining us the main challenges, methods, and solutions we can provide concerning seawater testing and nutrient analysis.
Thanks, Claudio. So, good morning, everybody. Welcome to the webinar. So today we will cover the topics that you can see here. We will give you a small introduction on the what are the nutrients that you can find in seawater, what's reported in the state of the art. One of the key points of the webinar will be the challenges that are that you can encounter when you perform analysis of nutrients in seawater. We will focus on the matrix effect. So what is this salt effect and how can we deal with it? We will also explore the chemistry on which the analytical methods are based and the elaboration of data. And finally, we will also give you an overview of the configuration of the instrument that we use for the analysis of nutrients in seawater. So, the nutrients that you mainly find in seawater are phosphorus, silicon, and nitrogen. You can find them in different forms. You can find it as phosphoric acid, phosphate, hydrogen phosphate, or as a dimer or polymer of the phosphoric acid. The phosphorus that you find in the seawater can come from a natural source, let's say. So it comes from phospholipids or phosphonucleotides that are the product of the metabolite of organisms that you find seawater. Unfortunately, also it can find from artificial source. So certain level of phosphorus can be can indicate a water that is polluted. So usually it's found close by industrial plants. For what concerns the silicon, you can find it as hydroxide or silicate, and as many of you knows already, the silicon is one of the main components of rocks, but you can also find in organisms such as diatoms, algae, fungi, or sponges that are made of silicon. Nitrogen can be found as a dissolved form, or as nitride, nitrates, ammonia, or nitrous oxide. It can come from the atmosphere. You can have nitrogen that comes from areas that are lowered in the level of oxygen, or as secondary secondary metabolites from the degradation of amino acids or proteins. So all this information you can find in this book. This is a very interesting reading that I suggest you all. And even if you are expert or you want to start from scratch, as I did, so in the Methods of Seawater Analysis book that is edited by Grassoff, Kremling, and Hernat, you can find a lot of topics. So it covers topics such as not only the chemical part, so the analytical procedure, the reagent, and so on, but it also talks about the type of matrices, and chemical physical properties of the matrices. It gives you also an overview on the instrument system, and also it talks about the statistical part. So what is the range that is analyzed, what is the precision, what are the limits of detection or accuracy. And it's this book, it reached its third edition, so it's quite update. So now, what are the challenges that you have to face when you perform analysis of nutrients in seawater? First, you have to consider the salinity. So you have a sample where you have dissolved salt inside, and this salt can interfere with the analysis of your nutrient. It can enhance or reduce the signal. And in some case, maybe you can think about to apply special calibration, dilution, and so on. Also, you have to consider that the nutrients that are found in seawater are generally considered as low concentration. And this concentration will not be the same all over the world. So you have to consider also the sampling variability. So you need something that can be adapted for the seawater at a different depth, or taken from a different location, or taken when there was a specific season. And then you have to think, okay, now based on this point, which kind of instrument can I use? I will explain that we can classify mainly in high hand and low hand. But let's start from the salinity. The salinity is the definition, is by definition what measure the amount of salt that are dissolved in the water. It can be expressed as PSU, that is a practical salinity unit, or as a gram of salt dissolved in 1 kilogram of water. So, as you can see from this picture, you don't have the same salinity all around the planet. The salinity can vary according to the precipitation. If you have an area that is involved in many precipitation, or is very dry, or you can consider, for example, seas that are close, like the Mediterranean one, or if you have polar area where you have ice formation, or unfortunately ice melting. So this is something that you have to consider. But it's not the only thing. The other thing is that you don't have the same concentration of salt, of salt and of nutrients in the same place, in the same area, but it will vary according to the depth, for example. So you can see here that we can go from nanomolar to micromolar concentration of the nutrients. And it's important to know what is the depth and what are the range that are acceptable, because if you have, for example, an excess of phosphorus, you can go through a process such as eutrophication, so the excessive growth of algae. Or if you have high level, for example, of ammonia, then you can have hypoxia. So in that place, you have low level of oxygen, and this will not advantage the life in the seawater. Also silicate, if you have very low concentration of silicate, Especially in very deep water, this is not a good indicator, because silicon in the deep water is used by diatomies, and these organs are responsible to capture the carbon dioxide. Then you have to see, okay, which kind of instrument I can use for the analysis of nutrients in seawater. We classify the instrument as high-end and low-end. An high-end instrument such as the ICP mass is a very sensitive instrument. It's very precise. It has very good repeatability. And the salt effect you can in some way neglect. Of course, it's an expensive instrument. It needs high maintenance, a lot of space. You can see from the picture, you also need space for the gas that you use in the ICP mass. And usually it requires high skilled end user. On the other hand, we have the continuous flow analyzer. They are more simple systems, so they don't have the same cost of the ICP mass. Also, they don't require high maintenance. They don't need a very big space. You can also put the Nexaflow under a fume hood, and it has the advantage that it can run at the same time more analysis. Of course, it doesn't have the same sensibility of the ICP mass. It doesn't have the same precision, and you have to consider the matrix effect. So what is this matrix effect or salt effect? Consider that in your sample, you have salt, and this salt can interfere with the signal of your analyte, your nutrient. Also, what happened is that if you use your as eluent water, distilled water, for example, what happened is that you have two liquids that have different densities, and when these two liquids reach the flow cell, the flow cell detects this difference, and you have what you can see in the graph on the right, this spike towards the down or up. So what you can do in this case, according on what the Grashoff book says, you can use correction function, for example, to compensate the salt effect, or you can use diluent, that have salinity compared or equal to your sample. So these diluents that you can use, they can be low nutrient seawater, that is the water that is taken from a distance from the coast that is around 100 kilometers and in a depth of between 10 and 30 meter. You can use artificial seawater. You just take, you can find on the internet receipt, or you can also find it commercially available. Or you can use the 35 gram per liter of sodium chloride water. You can see here you have very similar chemical physical properties. So what we do usually when we test an analysis is to first perform a calibration, so at least 5 points. From this calibration, we determine the curve and the correlation, so the square R squared. We also analyze blanks. So usually we put the same eluent that we use for the baseline in 2 cups at least with 5 replicate each. We calculate the theoretical LOD and NOQ. We validate the LOQ, the theoretical one. We determine the MDL, the method detection limit. And we validate the method by running, by analyzing the 20 usually and 80% of the maximum concentration of our range. Now, before to go deep into the methods, I would like to clarify, to highlight that you can refer to the parameter as element or as ion. For example, you can have a range of ammonia that is from 2 to 10 ppb of NH3, or from the correspondent value of NH3. So you can see here, you need to convert if you want to switch from ion to the element, or vice versa, you need to multiply or divide by a conversion factor. So I feel more confident in express everything as element. So let's start from the analysis of phosphate as expressed as PPO4. Here you can see what is the chemistry on which the method is based on. So you have that phosphate form a complex with heptamolybdate in acidic environment. This and in presence of antimony ions. This complex is then reduced by ascorbic acid to form a complex, another complex that is usually blue colored. So we measure the maximum absorbance at a wavelength of 880 nanometers. And the range that we test goes from 2.5 till 50 microgram per liter as PPO4. So here you can see the calibration curve. We have linearity in this range. You can also see the blanks that we run. And from the blanks, we determine the mean and the standard deviation. These two values will be useful to calculate, according to the ISO norm that I showed you before, the theoretical LOD, limit of detection, and the theoretical LOQ, the limit of quantification. We then need to test this 1.19 microgram per liter as limit of quantification. I try to test a solution at a concentration of 1.5, 2, but the one that was in the range of acceptability was 2.5 microgram per liter. From this 45, the sample, then we calculate also the method detection limit. And we validate the method with the QC. So the 20 and the 80% corresponding to 10 and 40 ppb. For the silicate now, so the chemistry, it's similar to the one of phosphate. You also have here a complex between the silicate in this case and the molybdate that is formed. This complex is reduced with ascorbic acid. The difference here is that you also have a third reagent, that is the oxalic acid. And oxalic acid is used because you can have interferences from the phosphate, because phosphate reacts with molybdate to form similar complex. With oxalic acid, we are sure that we neutralize, we depress the interference of phosphate, and we can measure the absorbance at 810 nanometer. In this case, the range that we covered goes from 2 to 500 microgram per liter as silicon. Here you can see the calibration curve. Also here we have linearity in the range that we defined. You can also see the theoretical LOD and LOQ calculated from the mean and the standard deviation from the blanks. So the LOQ that we wanted to test was the 2 microgram per liter, more or less. We were in the acceptability range. We determined the method, the MDL, the method detection limit. I didn't say before, as you can see here, this is based on the EPA norm and is calculated as the multiplication of a factor, the T student of the corresponding to, in this case, 10 replicates minus 1, times the standard deviation that we have. Then finally, as the previous method, we validate the method with the QC. So now, what about the nitrogen? Let's start from the nitrogen of the nitrites, NO2. So the chemistry for this method is based on a grease reaction. So you have that the ion NO2 reacts with this sulfanilamide to form a diazo salt. This diazo salt then form with this substituted ethylenediamine, this pink colored azo compound. That is detected between 520, 540 nanometers. In this case, we cover a range that goes from 0.1 to 50 microgram per liter as NO2. This is one of the most robust analysis. You have a very linear, good linearity in the range that we choose. The theoretical LOD and LOQ that we found are 0.03 and 0.09 microgram per liter, respectively. We validated the 0.1 as LOQ. We calculated the FDL, and also, as usual, we validated the method with the quality control. What about now the nitrites, the NO3? So the method is based on the same principle. We need first to convert the NO3 to NO2. And in the seawater, we do it using heterogeneous catalysis. So we have this cadmium surface on which it's absorbed copper, and this is the active catalyst that reduce in alkaline condition the NO3 to NO2. Now, for the buffer, you have different let's say, preparation. The ISO 29441 suggests the imidazole to use a buffer. The EPA 353.2 suggests ammonium chloride. They both work. So you can choose between this reagent. The range that we cover in this case goes from 1 to 300 microgram per liter as NO3. Before to start the analysis, you need to form the catalyst. So you use this column that you can see here, the green one. You need first to wash to remove everything that could be oxidated inside the column, and you use chlorhydric acid. Then you insert a solution of 2% of copper sulfate. You wait a little bit to let the copper to be absorbed on the surface of cadmium, and then you wash with your buffer. You try to keep your column inside your buffer, and you try to avoid the air to enter, to avoid the oxidation of the catalyst. What you can also do before to put everything in the buffer is to inject a solution 1-to-1 of buffer and a concentration of a solution at the concentration of NO3, the maximum one that you use for your range. So you close this coil to avoid air to get inside. Oops, sorry. And before to run the analysis, you need to see the efficiency of the column. So what we usually recommend to do is to prepare two solutions at the same concentration of NO3 and then NO2. you then you can make replicates, and you make the ratio of the average OD of each one. If it goes above a threshold, some ISO says 80%, other norms say 90%, but in this case, you can have an idea of the efficiency of your column. So after you are sure about your column, you can run your analysis. So here you can see the calibration curve, you can see the blank and theoretical LOD and LOQ that was found in this case. We wanted to validate the LOQ corresponding to 1 microgram per liter. Also, we calculate the MDL in this case, and we validated the method running the 20 and the 80% of the maximum of your range, concentration of your range. Last but not least, we have ammonia. So the chemistry on which is based this method use the reaction between the phenol and the monochloramine that is formed between the ammonia and the hypochlorite. I know that phenol is not the, let's say, most healthy solvent and reagent that you can use. In alternative, you can also use the salicylate. We just notice a slight difference in the sensitivity when we use the salicylate, but it always depends on the range that you want to analyze. So in our case, we are in the range between 3 and 100 microgram per liter as an NH3. So here you can find the calibration curve. In this case, we fit the data with the quadratic model. We calculate the theoretical LOD and LOQ. This 1.83 microgram per liter, we try to validate a concentration of 2.5, but the one that was in the acceptability range was 3. We calculate the MDL, and finally, we validate the method running the QC. So now, just to sum up, here you can find the configuration that we suggest for the next flow for the analysis of nutrients in seawater. You can see that we suggest, of course, if you want to run 5 nutrient, 5 consoles, you can run them at the same time. Also, you can use an autodilutor if you want to automatize the workload. And here you can find the code corresponding to the manifold for each nutrient. I just want to highlight that for ammonia, you can also have another method that is based on the fluorimetry. And here you can find the range. In this case, you can even lower the range that you analyze. Also, if you want to run the total nitrogen or the total phosphorus. So the total nitrogen is the nitrogen that comes from organic and inorganic source. So you need a digester, an UV digester, as well as from the phosphorus, the total phosphorus, because phosphorus can also come from organic molecules, such as phospholipid, pyrophosphate, and so on. Also, if you have matrices that you want to analyze that has a different salinity, so you want to have, for example, 2 different baseline, you can also use a double need, or we also have the chance to use the triple needle. So now I think for the hardware part, Claudio, the product manager, will give you more insight about that. So Claudio, the stage is yours.
Yeah, thank you very much. Yes, now let's see, because we spoke about our instrument, so what we can do, we already saw, and thanks Antonella for the presentation. And now let's see what the Nexa flow is. What is the segmented flow platform presented here and proposed by KPM? So as we can see, we really work hard to develop a system with a high precision peristaltic pump. And as you can see, we also introduce, we have two models, one with screen, one without the local screen. And the intended goal of this console, the one you can see here with the local screen, is to be able to work not only from the main PC, but also to have possibility for each single console to control the local settings, to see the peaks, the signals that are inherited to the flow cell during the analysis. And moreover, on all our consoles, as we can see just below the main screen, there is a status bar, really helpful because indicating in real time the status of the hardware. What does it mean? It means that based on the light coding, you can also from distance understand the status of the system. Moreover, we work very hard to develop a new reagent compartment where all the system is protected from any vapor effect from the reagents, because we know that sometimes those reagents could be quite strong. And so we are managing them to prevent affecting the system. And moreover, we introduce also as unique feature available the level sensing for the reagents. What does it mean? It means that the system is able to know in real time what is the amount of the reagent in each bottle, and this can help us to give you real-time information. And we can also use those information to verify if the required workload can be managed in a single run or not, because the intended goal for us is to really give you a true walk-away platform. That means possibility to start your run and just come back to see the results without need to be close to the system to give him the possibility to work and having all the needed liquids available. We also introduce, we will see better in the next slides, some new sensors that are really, really important because, as you know, in this case, we are working with segmented flow analysis, where the reaction stream is divided in multiple segments divided by air bubbles. And the bubble pattern is really important to define the proper working condition of the system. And this is why, as you can see, we have two bubble sensors, one on the entry line of the flow cell and one to the outlet of the flow cell, that are really, really important to check that the bubble pattern is constant before entering for the reading. And we have two cases. In one case, if we are working with the mechanical debubbling, means removing the high before the reading, we can check that at the outlet of the flow cell there is no air. Otherwise, if we are working with the electronic debubbling, means that we allow the bubbles passing through the flow cell, and is the software correcting the signals, removing the spikes from the air bubble. And in this case, we will check according to the inlet bubble sensor that the bubble pattern is also constant and correct when coming out from the flow cell. So moreover, we introduce also leakage sensors, very important because, as we know, those kind of systems are really, really requiring also intervention of the end user, because working with a peristaltic pump, tubes need to be replaced after a certain number of hours. And if also the operator is not working properly, we can control. And if there is any problem, we have leakage sensors for the peristaltic pump, on the manifold, on the flow cell, on the waste. And also we introduced the pump health monitor. What does it mean? We may know and control in real time the status of the peristaltic pump. The next slide, please. So, as we saw also from the previous slides from Antonella, we were having for all our parameters 2 wavelengths. One was referred to the measurement channel, one to the reference channel. Why? Because as you can see from this schematic, the signal will pass through the flow cell, and when out from the flow cell, the signal is split in 2 different beams, one going to the reference detector and one to the measure detector. What does it mean this? That with the reference detector, we may correct and manage any interferences that could impact on the quality of the signal, and so all the results you will obtain will be free from any interferences that could impact on the quality. What kind of readout modules we can install on our system is the standard colorimeter. We can work with the flame photometer. We can work with the fluorimeter, as we saw for the ammonia on seawater. And the readout is selected according to the manifold, to the chemistry you need to run. We have 2 flow cell. One is 5 centimeter and the other one is 1 centimeter. And as we say, we can work with 2 filters. The next slide, please. So as presented by Antonella, we have also 2 main models of autosampler. One is the circular one, and is the 104, and we have 2 models, 104S and 104. And mainly one can work in 2 ways, moving in 2 ways, and the 104S, while the 104 just working 1-way rotation. And then we have the XYZ, giving really high loading capacity for high throughput labs. As you can see, both of them can be equipped with auto diluter, and as Antonella already said, this could be very important because can increase the level of automation of the system. Why? Because when working with the auto diluter, we can fully automate the preparation of the calibration curve from the stock, so you are not having anymore the need of manually preparing the standards manually and then running. You can just load the stock standard on board, and is the system preparing all the calibration point and running them to have the calibration curve. What does it mean this? This means that not only the testing can be free from any human error, but also the preparation of the calibration curve, and moreover, all those samples that could be out of range can be automatically diluted by the system without any need for the operator to check the results and verify, manually dilute and rerun. So those options are very, very important. And you can find more information on our website, on the KPM Analytics website, in the chemical clinical web page, where there is a dedicated page for the NexaFlow system. And moreover, on the website, you can find the brochure of the system and also the brochure dedicated to the seawater testing, where all the information presented today by Antonella have been reported in the dedicated brochure. So we are now ready for the Q&A session. Thank you very much for attending this webinar, and we really hope to see questions from your side. And of course, we look forward to meet you all in person at Analytica 2026 in 2 weeks, where we will have a dedicated booth that you can find all the information here in the dedicated banner. Let's see in the chat if there are questions arriving. don't be shy. So if you want, type, and we will be very happy. So one question arrived. Is also working well in fresh water? Of course, yes. Yes, and all the methods we saw today dedicated to seawater testing can be also used for freshwater testing. And of course, thanks to the interchangeable flow cell. Okay, Delphine?
So the
So
answer is yes. In freshwater, it works quite well.
yes, because of course, when we are increasing the LOQ needed, it's something we can easily address because the seawater testing is one of the most stressing testing for wet chemistry instruments, and the positive point of the segmented flow continuous flow system is that we may have interchangeable flow cell that allow us, based on the number below, increasing the reading path, so increasing the sensitivity of the system. So when we are moving on high ranges, it is much more easy. There is another question. Are there any EASE or EPA reference method for the various methods used in the seawater testing? Of course, yes, because the Grashof method, Antonella, I think if you want to provide a bit more detail about this.
Yes. So we base the test on the Grashof, but you also have the ISO and IPA that works for that describe the quality of water. So also seawater, and you can also find the norms in both case, ISO and IPA. I know that someone is more confident with ISO, other with EPA. But if you search on the internet, you will also find this reference.
There is another question related to how we can manage the salt if they could get crystallized in the system during the analysis and if they can block the tubings.
Well, I guess it can happen because it depends from the water that you are using. The advantage is that of the segmented flow cell is that you can also see what's is going on in the system. So in case you can see some precipitate clogging the system, you can visible notice that, but you will also have, of course, contrast result in your analysis. So also something that we monitor is the waste. So we need to have the regularity of the bubbles also in the waste. If you don't have regularity also there, it means that something is blocking or clogging the system. Let's say that one of the advantage of to have the segmented flow is that you have small segment. So as far as for what I've seen so far, it never happened, even with the very concentrated water to have precipitation. What you can see for the precipitation, for example, is if you have some metals, transition metals in your seawater that can precipitate at a certain pH, for example. But you have to have very high concentration of this metal transition metal. So
There is another question concerning possibility to share all details concerning LOD and LOQ for all parameters for seawater testing. Of course, yes, there are already application notes available over Search Center for all our partners that can be downloaded and shared with the end users. So they are already available. And as we said in the previous slide, there is a dedicated brochure for seawater testing with NexaFlow, where all the LOQ, LOD, and MDL have been listed. Thank you, Antonella. Is the document you can see on the right of this slide, Nexaflow for seawater testing. And over here, you will find all the information concerning each manifold, concerning LOD and LOQ. And moreover, you can also find what is the suggested configuration for the system to cover all the parameters with the Nexaflow. There is another question. When we using our CFA test seawater, except using blank seawater as diluent, are there any other methods?
Well, what I don't know if I got the the question.
It's very an open question, this one.
Yeah, well, you can use you can just run your calibration, but I guess you need to check the blank, let's say, to check your eluent as well. This is something that you can do for every kind of analysis. It's not only in the continuous flow, but also HPLC, GC. Sometimes you need to see what's in your baseline. So well, you can check your blank with ICP mass if you have the chance, or other technique. Um, I hope I reply correctly to this question if I got the meaning. So,
And please, if not, type in the
yes,
more
please.
detailed question. There is another question concerning interferences, as we already were mentioning about metals or any molecules present in the matrix and how to eliminate them. We already spoke about possibility to have the correction with the reference filter that can allow us to read with another wavelength the reaction to see if there is something interfering with the color we need to manage, and those will be automatically corrected by the system. So the final absorbance you will see for each test is not only the absorbance we are reading with the sample, with the measurement channel, but is already corrected with any interferences we can detect with the secondary wavelength with the reference channel.
Just to add something to this, Claudio, you also have chemical methods, let's say, that you can employ for the interferences. For example, there is in the book of in the Bible of Grashoff, it's described how to in the analysis of phosphate how to depress the interference caused by chromium or iron. So you can also, in this case, for example, exchange the R1 and the R2. So use the as R1 the ascorbic acid instead of the molybdate, and the other one will then convertly swap consequently. So there are methods, also chemical methods, that are suggested to depress these interferences.
There is another question concerning the bubble sensor. So is the function of the bubble sensor included as a standard on Nexaflow, and can this function be turned off? So the answers are yes for both the question, because all those sensors are by default including Nexaflow. And of course, if you have the Nexaflow 450, the one equipped with the screen, with the local screen, as you can see in this slide, there is one console on the left without the screen, one console on the right with the local screen, which is Nexaflow 400, Nexaflow 450. So in both cases, from the embedded local screen or from the main PC, you can activate or deactivate the sensors. So any sensor can be independently managed by through the software. There is another question concerning ammonia, if it is possible to run ammonia using gas diffusion, and the answer is yes. And gas diffusion is also available for other parameters like cyanide, because cyanide also can be done using UV digestion and distillation, or UV digestion and gas diffusion membrane. So the general answer is yes, gas diffusion membrane can be used on extra flow. So I think this is something related to the previous question. If the blank seawater is used as a diluent solution, how can the influence of other ions such as potassium ions, calcium ions that do not exist in the blank seawater be eliminated? So how would we manage removing those ions?
Well, these are interferences are intended as interferences. So for each method, you have what it can interfere in in the analysis, such as if you are analyzing the silicate, you have phosphate, for example, that can interfere, and then you have um, um, the method is specific for the analysis of that nutrient. So you can chemically or with hardware neglect the effect of these interferences.
I think it would be helpful if you want to go back to show one of the methods where they can see
Yeah, of
the two
course.
wavelengths plus the detail about the interferences they may have from the parameters. So all those information have been reported here on those slides.
Yeah, for example, here you can have for the analysis of silicate, you have phosphate that can interfere, or you have metal, transition metal that can interfere. So you can use the chemistry to suppress these interferences, such as in the case of phosphate. Or you can also have for transition metals. I don't remember exactly what are the chemical approach to depress these interferences, but you can in some way reduce the effect of these in your that can interfere in your analysis.
And as you please, sorry.
Yeah. You
As
can.
you can see, you from the diagram you have here, from the Jory diagram, where you can see measurement and reference, and moreover from lambda measurement and lambda reference, you can see that we are using one wavelength to read the reaction and one wavelength to read any interferences that may impact on the reading of the final color of the chemical reaction. So just to fix what we were managing also with the previous answers. There is another answer related to the cadmium coil. So do we have to reactivate every time? And what is the frequency of change in the cadmium coil? So in this case, I would like to add one important information, that the cadmium coil could be also managed with, if you can go back with the slide, with the automatic valve. What does it mean? That you don't need to manually swap if you want to pass through the coil or not. The system can be equipped with the automatic valve, and based on the chemistry, because this lot of time the same manifold can be used for both NO2 and NO3 testing, and the difference is just if we are passing through or not within the cadmium coil. And in this case, the valve is automatically managed by the system. Concerning the reactivation time is not needed. It depends also on the workload and the matrix you are going to analyze with the manifold. So there is no a unique answer to this point. So there are a lot of variables that can define how often you need to reactivate and when you need to change. So as Antonella already said, the correct approach is to run daily based the RDT to check what is the status of the heart concerning the reduction yield capability of the column. And if you can see that the reduction yield is not the one you are expecting, you can run the reactivation of the cadmium coil and then run again the RDT. And if everything is fine, you can go ahead calibrating and running samples. And when is needed to change the cadmium coil? When, after performing also more than one subsequent reactivation, the reduction yield is not reaching the expected behavior. At that point means that the internal copper layer have been is not able anymore to reduce the NO3 to NO2. And of course, also the concentration, the range is also important, because as you can imagine, the amount of NO3 that need to be reduced to NO2 can also impact on the behavior of the cadmium coil based on the life cycle of the coil itself.
If you want to be sure that your column is working fine, what I usually suggest is to have one sample with NO2 and then NO2 or an NO2, and at the end of your work plan, and then you can check if the column is working fine or not.
Yes, because the RDT, this is a good point, Antonella, can be used before starting the routine to check what is the status of the heart concerning the cadmium coil, what are the working conditions. But moreover, you can also add those RDT controls in between of your samples. In this way, you can constantly monitor what is the reduction yield. In this way, you can be 100% confident that the results you are obtaining are correct, because you can monitor the reduction yield in real time.
So here you can see I just put at the end one control to check that everything was fine.
So it was the last question. It seems there are no more questions. We have still 3 minutes remaining. And thank you very much for all those questions, because I think could be interesting for all the attendees to deepen those topics. So if there are no questions, let's say we can just say thank you everybody to join this session, to give us the possibility to introduce you to our platform, to our instrument, and to the seawater testing segment. And we really hope that we have been able to